check. 1 second. All right, a quick sound check. Let's see. Increase the signal a bit. Sound check, sound check. All right, should be fine, I think. Should anyone be watching and from the Discord channel, please let me know there. If audio is chopping up, I'll try and fix it on my end. There have been some issues in the math sessions with the audio. I think it may be my audio interface. I might have to get a new one. All right. Okay, so let's see here. I'm sharing my screen, so should be able to see my screen soon. Just make sure everything's on. Screen share your entire screen. Yes, share my entire screen. Thank you. All right. So here we are. We're starting. So this is CLRS, Introduction to Algorithms, and we covered chapter 1 last time, where the authors just introduce the role of algorithms in computing, what constitutes an algorithm, why I may want to use it, why do we care about algorithms, etc., etc. Essentially, you can think of it as a fancy term for a sequence of steps, and the sequence has some sort of an input and a well-defined output. So a well-defined input and a well-defined output, and we have a recipe to get from this input to this output, and we called such a procedure an algorithm. So now we go to chapter 2, called Getting Started, and chapter 2 essentially introduces ideas about pseudocode, which is what we're going to see in the rest of the book, on an example, and the example is the insertion sort algorithm. So we're going to go over insertion sort today, and we'll even code it up, or we'll try to. I don't promise to do a good job, but that's the purpose of the stream, is we do it, or I this is a learning procedure for me as well, learning process for me as well. So what is pseudocode? First of all, pseudocode essentially is a programming language independent way of writing an algorithm. Okay, we try to use more of mathematical notation combined with the English language to produce a step-by-step description of the process of the algorithm without relying on constructs that are language specific. Okay, because different people code in different languages depending on their work, etc. So we don't want to focus completely on the programming language, but we want to focus on the ideas. And so a key concept here that students often miss, in my opinion at least, is that they think once you go through a book like this, you're a master of algorithms and you're going to just crunch through every assignment, every problem, etc. This is not quite true. This kind of a book is essential for understanding the algorithm, but you need to practice coding it. And that requires picking a language, okay, and coding these algorithms. If you're a math major or if your education is in mathematics, then you know firsthand that it's one thing to actually go through a theorem, prove it, gain a theoretical understanding of it, but it is also essential to try and do some exercises, some proofs involving that theorem to become comfortable with it. It's the same deal with this. You want to code the algorithm in your language of choice, because when coding, a lot of practical things come into play that you don't necessarily think about it in the idealized world of pseudocode and mathematics. So that's my 2 cents on that. So let's get started. Sorting problem and the insertion sort. So let's open this guy here. Let's talk about the sorting problem. So what's the sorting problem? As we said, every algorithm requires a well-defined input and a well-defined output. So what's the input in this case? The input for us is a list, and just for simplicity, let's assume um, let's assume we have integers here, okay? So we might have some integers, let's say -3, 4, 0, -5, 7, 8. So this is our list, and the goal, the output should be the same list, but in the correct order. Okay, so it should be -5, -3. What do we have next? We have 0, we have 4, we have 7, we have 8. This should be my output. Okay, so this is our intuitive definition of sorting problem. Notice I have not defined any specific algorithm yet. There's no mention of that, of an algorithm. I'm just telling you what the problem is. Here's an input, an unsorted list of numbers. I want to get that same list in sorted order. Give me an algorithm that'll do this. All right, now let's go back to the book and see what the formal definition of this is. A sequence of n numbers. Here they are, A1 through AN. Okay, that's our numbers here. These are our numbers, A1 through AN. This can be our A1 here, all the way to AN. And the output is a permutation. Permutation is a mathematical term meaning reordering of those same numbers, see, of the input sequence, such that, and notice this constraint. We have a constraint, and the constraint is that these numbers, each one of these values should be less than or equal to the next one. So in our case here, what that means is -5 should be less than or equal to -3, should be less than or equal to 0, should be less than or equal to 4, less than or equal to 7, less than or equal to 8. And once you write this on the example, it is clear why we need this constraint. This just means that our numbers are in order. Okay? As you can see here, everything is going in order. Now, why less than or equal to? Because our list might have duplicates, right? I might have two -3s here, or two -5s. Suppose I have two -5s. So in that case, I can't just say -5 less than -5. That is false. But once I do less than or equal to, then I've allowed for the possibility of duplicates in my list of numbers. Okay, so it just takes care of this corner case of having duplicates. All right, so that is our formal definition of the problem. Now, so this is a key notion here, in-place sorting. What does that mean, in-place sorting? Let's go back to our board here. Well, I could tell you this. I could say, let's take our input, and I'll rewrite it, -3, 4, 0, -5, 7, 8. This was our input list. And I can tell you this. Let's make another array here, another list. I'll call this aux for auxiliary. Same size. Okay. And then what I can do is I can go through these values, through each one of these values, throw them in this auxiliary list through some procedure. I don't care what that procedure is, but I could imagine that I'm going to use this auxiliary list first. I'm going to fill it first, and then here I'll have my output, which will be some new list, and then from this auxiliary list, the numbers will come in their correct place from the auxiliary list. Or you may say, okay, I don't even need an auxiliary list. Maybe I can do this. Maybe I can have an input list of numbers. Let's do -3, 2, and then -7, let's say. And then my output will be a whole new list where things will be in order. Right? So notice that this is my input, this is my output. The output is a new list. It is independent of this original one. We make a new list where these numbers are in order, and the user gets back this new list. This is not in place. Not what's called in place. Why is this not in place? The reason is that I made a new array. This guy here was a new list. In place means that when you give me the input of -3 to -7, I start modifying I start permuting these numbers inside of this same list. I never make a new one. So you can already see that in terms of memory of your computer, this is more efficient because I'm never actually making a new list. I don't have this auxiliary list. I'm permuting these numbers, all these numbers, some kind of permutation. However I decide to move them around, I'm moving them around in this same list, and then the same list goes out to my user, out of the algorithm, in other words. Okay? And this is in place. In other words, when you're sorting your numbers inside of the same container that was the input, that's in place. When you're making a new container into which you're putting these values in the correct order and then returning this new container to the user, this is not in place. So when we get further in the book, this concept will become more and more important. Okay. All right, quick check just to see if that everything works. Let's go here. Yep, it does. Great. Okay, continuing on. So here's an example of how the algorithm works. Let's first try and understand the pseudocode. Here is the pseudocode. So notice pseudocode always starts with the name of the algorithm and the input. So we can just guess, although they do mention what A is right here, but I mean just reading the pseudocode, we can tell that A is our list of numbers. Now look what they do. They say start from 2, go to the end of the array. So okay, this pseudocode, this is kind of important. This is going to trip a lot of people up, so I'm going to mention it. In computers, things contain the memory location or just contain things in containers in general are usually indexed starting 0. So let's say if I have these 3 numbers, this is at the 0th position, this is at the 1st position, and this is at the 2nd position. Okay? If you've never done any sort of algorithms or if you've never read CS books, this is kind of crazy. And why would you start counting from 0? But that's CS. So we start counting from 0. Now, looking at this pseudocode, it seems like the count starts from 1 and not from 0. So I'll double check this later, but let's just assume that's the case. And then maybe in the end we'll reach a contradiction and our assumption will be wrong. But for now, let's assume that's the case. Let's assume that they start the count from 1, which means what? Which means in this example here, this will be the element at location 1, element at location 2, element at location 3. Now, what does the algorithm tell us to do? It says loop through all the elements inside of your array, starting from the 2nd position all the way till the end. So I'm going to loop through all the elements starting from the 2nd position, so the 5 and the 7. So we start from the 5. What do we do with the 5? Get that element from your list, the element at the jth position. Remember, j starts from 2. So at 2, I have the 5. In other words, I get the 5 and I put it inside a variable called key. So I have a box here. Let's call this box key. Let's put it here. This will be my key. And currently, key is 2. What happens next? Insert a subscript j into the sorted sequence from 1 to j minus 1. Okay, sorted sequence. So let me explain this for a second. So the algorithm keeps track of an index j, this j here. What does this j stand for? Everything to the left of j is assumed to be already sorted. Everything to the right of j, including j itself, is assumed not sorted yet. Okay. So notice he says insert a subscript j into the sorted sequence from 1 subscript 1 to j minus 1. All right. So let's see. It's supposed to be 5 and not a 2. It's the element at index 2, not the index, but the element at index 2. So it's the 5. So what do we do now? So now the algorithm says, set a new variable, take a new variable I and set it to the j minus 1. Well, remember what j was. J is currently at 2. That means j minus 1 is 1. So I is currently 1. I is currently 1. What do we do next? We say as long as I is bigger than 0 and the element in the ith position is larger than this thing we called key. And what did we call key? We called key the element at the jth position, this 5 right here. This was my key. So as long as the element in the ith position is larger than this key, this 5, what do? I move. So I take the current element that is larger and put it in position. I put it in the next position. Let me demonstrate this on picture. Let's take a let's do this. Suppose I have 7, 5, 3. So this is position 1. This is 2. This is 3. So j starts from 2. Remember. So we're gonna take this number here. Next, I is set to this position, this index. So the element at the ith position is 7. Now the algorithm says as long as that element is bigger than my 5, and we can see that it is, 7 is bigger than my 5. What do? Into the ith plus 1 slot, into this slot, I put the element at the ith index. So this number I put here. Okay, so in other words, I'm gonna have 7, 3, like so. 7, 3, right? The number that was at the ith position, we put at the I plus 1th position. And remember, this 5 we've saved in this variable called key. We did that in the beginning of the, right here. We saved that, right? Then I gets reduced by 1. But when I gets reduced by 1, I becomes 0. And our algorithm only works when I is bigger than 0. This loop only works when I is bigger than 0. So as soon as I becomes 0, our loop stops. So this loop stops. And then into the I plus 1th position, we're going to put the key. Okay, so notice I is now 0. Our loop has stopped. I is 0. That means I plus 1 is 1. And so it says into that first elements box, put the thing you had saved before. So the 5 in our case. So the 5 now gets put here. So essentially this whole thing said do this swap. So we did this swap. Now j moves over. Now j is pointing to this element. So save this inside the key. So key is now 3. Right? Key is now 3. Now I gets set to 1 less than j. Right? Let's go back here. I get set to 1 less than j. That's line 4. So I is now 2. We get that element. The element at the ith position is 7 right here. And we're going to compare it with the 3. Notice we're now doing this loop. Now this loop says we're going to do we're going to do lines 6 and 7 only if the element at the ith position is larger than my key. Well, my key is 3. The element at the ith position is 7. It is larger than my key. We enter the loop's body. What does the body say? It says, into this I plus 1th box, put in the element in this ith slot. In the ith slot, I have 7. I plus 1, I have 3. So the 7 goes into this 3's place. So after that step is done, we have 5, 7 here and 7 here. So in this 3's place, we've put the 7. And this is, and I gets reduced by 1, right? So I is now pointing here. Now the same procedure happens again. It says, is AI bigger than my key? Is AI bigger than my key? Yes, it is. Key was 3, right? Key was 3. Is 5 bigger than 3? Yes. So into the I plus 1th slot, we put that a ith element, or ith element of A. So in other words, into this slot, we put this 5. So now my list looks like this: 5, 5, 7. I gets reduced by 1 again. So when I gets reduced by 1 again, I is now 0. But notice our loop only runs when I is bigger than 0. So I is now 0. Our loop stops. We jump to line 8. And it says into the I plus 1th slot. Well, if I is 0, I plus 1 is 1. So into the first slot of A, put the key. What was my key? My key was this 3. So into this box right here, I'm going to put 3. And so finally, my list becomes 3, 5, 7, and it is sorted. Okay. So, all right. So first pass at the algorithm, somewhat still confused. We followed it line by line. It's all worked out, but it's not quite clear how it worked out. Let me try this again. Now I have better intuition. Let's do this. Let's do 1, -1, 0, 3, -2. This is my input. I need to sort this. My algorithm says you start from the second position and you're going to go all the way till the end. Okay. So we start from this -1. From this -1. All right. So J is -1. I starts 1 less. So I is here. Or actually the element at the jth position is -1, and the element at the ith position is 1. So now we compare. We say as long as I is bigger than 0. Well, what is I? I is 1. It is bigger than 0. As long as I is bigger than 0, what do? We compare it with my key. So I compare this element with -1. Is it larger than -1? Yes, it is. Put it in -1's place. So right now, after this step, I have 1, 1, 0, 3, -2. And this -1 has been saved inside this key, remember? Okay. The procedure continues. I becomes 1 less. I is now 0. So because I is 0, our loop stops. And into the first slot, we put the key. What was my key? It was -1. And into this first slot, I put it. So now I have -1, 1, 0, 3, -2. So this subproblem is solved. What is a subproblem? We can define a subproblem for each value of j. We started with j equaling 2, and we solved the subproblem by looking at all the numbers to the left of this j. To the left of this j. So now we can assume that everything to its left is sorted. As we can clearly see, -1 and 1 are sorted. And that's what this comment on line 3 alludes to. It says, insert A sub j into the sorted sequence from the first position to the j minus 1th position. Okay, so this is now sorted here. All right, j moves over to 3. So j is 3 now. What is my key? My key is A sub j. So that's 0. That's my key. My I is this second. So this is my j index. This is my I. So AI is 1. Right? So i's value is 2. 2 is bigger than 0. Our comparison begins. Is this 1 bigger than 0? Yes, it is. I'm going to move the 1 over. So I'm going to have negative 1, 1, 1, 3, negative 2. Right. I gets reduced by 1. I gets reduced by 1. I is now pointing here at the first element. Is the first element bigger than this one? No, it's not, right? Negative 1 is not bigger than 1. Our loop stops because notice one of our loop's conditions is that that element at the ith position has to be bigger than our key. Our key was 0, and negative 1 is not bigger than 0. So the loop stops, and it says into the I plus 1th position, insert your key. So here's I plus 1th position, and in there we put the 0, and we get negative 1, 0, 1, 3, negative 2. Okay? So now everything up to here is sorted. So J moves 1 over, right? J moves 2. So everything up to this point, the first 3 elements are now at this point sorted. J moves over here. I moves over here. So we start comparing. We say, is 1 bigger than 3? Well, no, it's not. The loop immediately stops. We never even enter the loop because this element at the ith position is not larger than our key. That is 3. So the loop stops. J moves over to this number, negative 2. I is now pointing to negative 3. Or positive 3, excuse me. And we start our comparison. We say, is 3 bigger than negative 2? Yes, it is. Right? Put 3 in that position. So we have negative 1, 0, 1, 3, 3. Okay. I goes 1 to the left. So this I is here now. Is 1 bigger than our our key? Remember, our key is negative 2. Yes, it is. Yes, it is. Put so what do we do? As long as it's bigger than key, put it in the next slot. Okay. Well, that means 1 will be put here. So we have negative 1, 0, 1, and now this 1 goes here, 3. Okay. I goes here. Is 0 bigger than our key? Negative 2, yes. Bring it over here. Negative 1, 0, 0, 1, 3. I goes over here. Is negative 1 bigger than our key? Yes. Move it over. Move it over. Negative 1, 0, 1, 3. Okay. Now I goes 1 over, and it's now 0. I is now 0. Well, when I is 0, what happens? Our loop stops, and into the first position, we put our key. Our key was, of course, negative 2. And so this first position right here becomes negative 2. There we go. And we can see that our list is now sorted. All right. So again, this seemed to work. I mean, we started with a list. We followed the steps. And we ended up with a sorted list. But let's try to understand what is going on here. What are we doing at each step, really? What is our algorithm doing? So it seems as though I'm searching for a place to put my key each time. So if I have a list of numbers, let's just make sure there are no duplicates for now. There we go. So when I pick a number, and remember we start with this. We start with j equaling 2 here. What I'm doing is everywhere to the left of this j, I'm trying to find the correct position for this j. Now, negative 3 is smaller than 4, so as far as we know, just looking at this left side, just these two elements, 4 is in its correct position. So everything's good there. So j moves over to 1, And now I'm going to look at these three elements. I'm completely ignoring, let's put the comma over here. It looks weird there. I'm completely ignoring the right two numbers, and I'm looking at the left side of the list, and I'm trying to put 1 in its correct position, right? Well, how do I do that? Well, first, how do I find its correct position? I first compare it with 4, and I see that 4 is larger, so I know 4 should come after 1. So I move, first I save this one somewhere, put it in a variable called key or something. I know 4 is larger, so I should toss 4 over here, which I do. So I have -3, 4, 4, 5, -7. And remember what I'm doing. I'm trying to find the place where this 1 should be. Now I figured that it's not here, because 4 was larger. We put the 4 here, right? Then we compare that key of 1. We compare it now with this number, with -3. Is -3 larger? No, it's smaller than the 1. It is smaller than the 1. So I know that my 1 should be after this -3, right? So it should end up here. And so into this slot, I put my key of 1. And now I can see that this part ends up sorted. So now that I've sorted this part for this j being this position here, I can now introduce a new element, the 5, right? So I introduce a new element. So now I'm going to be looking at this list. 5, I completely ignore the -7. So now my j is this position here, and I need to find the correct slot amongst these 4 numbers for the 5. Now remember, I know that these 3 are already sorted. So I compare the 5 to 4, and since 5 is larger than 4, I know that it's larger than everything to the left of 4. Hence, it's sitting in its right spot. It's in its right place, right? So remember, I is set to 4 here. We're comparing this 5 to this 4. And because 4 is smaller, this while loop would immediately stop. It would jump to line 8, which would say, put the 5 into the position right to the immediate right of I. Here was the ith position. Put the 5 to its immediate right. In other words, leave it in its place. It's in the correct slot. Good. So now we know that these 4 numbers are sorted. Now we're ready to introduce the final number. So we have -3, 1, 4, 5, and now we introduce the -7. So now this position is our j, this position is our I, and we need to find the right place for this -7. So we start our comparison, right? And keep in mind, we know that these 4 numbers are sorted. We know that. Okay, so -7 gets compared to 5. Is 5 larger? Yes. So I know 5 should come after -7. Right? This should not be the correct place for -7 because the element to the left of it is larger. So toss it over here. So 5, 1, 4, 5, 5 goes here. Great. Now we compare it to this element, right? Because if this jth element, if this -7 happened to be larger than 4, I would know that its correct position is immediately to the right of 4. So it would go here. So I compare, I say, is -7 larger than 4? No, it's not. 4 is in fact larger. That means 4 should be to the right of this. Now this is not the correct place for -7. 4 should be there. And so 4 goes over here. This becomes a 4. 4, 5. Okay. And now our I goes over here to 1. And now we compare. And -7 is smaller than 1 as well. So 1 is going to be larger than it. So it should move 1 to the right. Okay. And this procedure continues until we compare. Now until we compare -7 to -3. And it's even smaller than -3. it's smaller than -3. Um, and so let's do that comparison here. When I comes here, when I is over here, um, what's going to happen is when we compare -7 to -3, -3 is larger, so -3 is going to move 1 over. I know -3 can't be the leftmost number. It is larger than -7. So it moves 1 over, opening up one free slot, the leftmost slot. So -7 has no choice but to fall in that leftmost slot. Now, why do these numbers move to the right one space? Why not 10 spaces? Why not, why not 10 spaces? Because these numbers, the numbers are ordered. The numbers to the left of this bar are in their correct order. So if I'm moving -3 to the right, I cannot move it past 4. It's I know it's smaller than the 4, so it can only move one step until it hits the next number. It can't pass that next number. Otherwise, I would mix up my order. Okay, that's why at each point these numbers are moving only one step at a time. All right. So, all right, so better. This is better. So it seems, it feels to me like I'm starting to get the procedure. And as you guys go through this process, you'll naturally get a lot quicker at this, and you will start understanding the algorithms immediately if they're not too complex. Of course, you'll start catching them immediately, aside from a few corner cases, and you won't need an hour to go through an algorithm. But since this is our first introduction to the very first algorithm, I want to go through this sort of thought process. And remember, if you cannot clearly explain an algorithm to yourself, and this doesn't just have to be a CS algorithm, I mean any subject, if you cannot break it down to yourself clearly, you have not fully understood it. If you can't come up with examples, if you think you got the theory, but you're struggling to come up with examples, you haven't understood it. This was a technique Richard Feynman, the famous physicist, used for himself. The way, when he learned new material, on piece of paper, he would write down in his own words examples of that concept. And the way he knew that he understood the material was he was able to come up with his examples, and he was able to explain it to himself in his own words. So that's what I'm doing here. I'm showing you this process of explaining to myself the process. So I kind of get it, right? But it's still messy. So I haven't fully understood it. I've understood it better than before, but not fully. So we do it again. Let's do 3, 1, -2, 2, -1, like so. So this is my input. Now, let's look at a few things here. Question: why does J start from 2? Why not from 1? Why do I not start my comparison from the very first element? Well, because remember that when I pick an element, suppose I pick the first one, I'm trying to find its place. Amongst which elements? Amongst the elements starting from the first, leading up to that element, not including that element. So for everything, so here, let me show you in this example. If I pick an element, what I'm trying to do, I'm trying to find its place in here amongst these two elements. At this stage, when my j is here, at this stage, it is assumed that everything to the left of this bar is sorted. And what I'm trying to do is I'm trying to find the correct place for this -2. If I start my search with the 3, if I start my algorithm with the 3, so if j is pointing at this location, there is nothing to the left of 3 for me to put 3 in. There is no sorted sub-array here where I should search for 3's place. So it's kind of a waste of time, right? There's nothing to search. So what do? I start I start from here, from the second place. And I assume that everything I put the bar right there, and I assume that everything to the left of the bar is already sorted. And that's true, right? If you have only one element, it is obviously sorted. You can't one number cannot be out of sort, so to speak. One number is already sorted. So that's the reason we start from 2. Now, and this comment 3 here is very like nonchalant here, but it's absolutely important to understand. Look what it says. It says insert a subscript a j here, this key here, this number we're looking at. Insert it into the sorted sequence starting from the first position ending at j minus 1. That's exactly this bit here. So we're trying to insert this number in this sorted, keyword, sorted bit here. Now, the process starts. We see that 3 is bigger than 1. 3 is bigger than 1. So we know that this initial position cannot be the 3. 1 is smaller than it. So if anything, 1 should be there. So 3 moves over, takes this 1's place. 3 moves over, takes this 1's place right here. And 1 ends up here. Stage 1 complete. And by stage 1, this is the stage when j equals 2. Okay, that's right here. Now we go to the next stage. During the next stage is when j equals 3. So now when j equals 3, what do we have? Here is our third element. This is our j. 2 minus 1. Now we're assuming that everything to the left of this bar is sorted. These 2 elements are now sorted. And our job again is to find the place of this minus 2 amongst these 2 elements. Okay? So again, we start. We compare the negative 2 with the 3. 3 is larger, so I know 3 has to come after negative 2. Right? This cannot be the place where negative 2 is currently is not the right place because 3 is larger. So 3 takes its place. 3 takes its place. Like so. Then we compare the negative 2 with this 1. Well, 1 is also larger. Right? So I know negative 2 cannot be here either in this slot. Why not? Because 1 is larger. So let's push 1 over there. 1, 3, 2, minus 1. And so negative 2 has only one place to go in, that this initial slot. That's it. So negative 2, 1, bar 3, 2, minus 1. So this stage is complete. Now we go to stage 4, or rather the next stage when j equals 4. And now we have negative 2, 1, 3. Now remember, j is the 4th element, so this 2 is my j, and so everything to the left of that is assumed to be sorted. There we go, and it clearly is. So the process starts again. So we're again trying to find the place of this 2 amongst these 3 numbers. Right? So 3 is bigger than 2. Currently, this is not its place. So 3 is larger. 3 is going to sit here. 3 is going to sit here. Now I'm asking, is this 2's place? How do I know that? I compare it to 1. Yes, it is, because 1 is smaller than 2. So this has to be 2's place. So I'm going to have negative 2, 1, 2. Then I'm going to have 3 and minus 1, like so. And finally, the stage, so the stage when j equals 5, negative 2, 1, 2, 3. minus 1. This is my fifth element. That's where j is. So that's the bar, and these four elements are assumed to be sorted as they are. And we start the process again. I need to find the place of -1 in here if possible. If not, it'll sit in its place. So is 3 bigger than -1? Yes. 3 in our minds, sort of, we imagine 3 moves over. Now, when you move 3 over, think about it this way. You've now emptied this slot where 3 used to sit. So now the question is, should -1 go there? Well, we compare it with 2. 2 is larger. So no, -1 should not be here. 2 is going to take its place. Now you can imagine that 2's slot is empty, and we're asking, should -1 be here? Well, we compare it with 1. 1 is larger, so no, 1 gets pushed up. So now it frees up its slot. So now the question is, should -1 sit here? Well, we compare it to -2, and -2 is smaller than -1. And so the answer is yes, -1 should sit here. And so our final answer becomes -2. This -1 that we just put here, 1 got pushed up, 2 got pushed up, 3 got pushed up. Done. We're sorted. Okay. So again, the moral of the story is, starting from the second position in our array going till the end, we pick an element, we pick the jth element, we save it inside a variable called key, and now our job is to put that key into the sorted part of the array. So the part to the left of this bar, okay, from 1 to j minus 1. Now, notice that if this was a 0 instead of a 3, if this was a 0, 0 is not bigger than 1, so 1 is bigger than 0. So we'd know that 1 is in its correct place, so we wouldn't need to do anything, right? So it would stay. And the way that's coded up is, notice that, so j is 2, I is 1, and because this element would be smaller than kr loop, we would never enter our loop, and it says into the I plus 1th element, in other words, into a subscript 2, put your key. Well, this is the 2, second position, I mean, this is it. So in here, I want to put my key. My key is 1. So in other words, it was 1, and I put 1 in there, so nothing has changed. So that's how the algorithm accounts for this possibility of this number that we're looking at never having to be put anywhere to the left of this bar. So that's how the algorithm accounts for this number staying in its place. It just says, okay, this is your j, this is your I. If it so happens that this ith element is not larger than this, then into this I plus 1th position, put that current key. So we'll into this position, we'll put a -2, which means just keep it the way it was. Okay, so it makes sense. Now we kind of have a better understanding. If at this point you still don't, I strongly suggest you do this again. Make up another example. Make edge examples for yourself. What if my array has a single element? How would that work? How would that work? Well, think about it. If j starts from 2 according to our algorithm, right? I don't have a 2. I have a 1. I don't have a 2. Does that mean my algorithm is broken? Well, you might say yes, because if I try to access a second element, the computer will break and say the computer will throw an error and say you don't have a second element. You only have one element in there. So there are these edge cases. You might say, okay, if my list contains one element or no elements, in fact, if it's just the empty list, just return the list as it is. There's nothing to do. If it has more than one element, then we do the sorting. Okay. Now, let's give this part a read here, because some of this stuff is actually important and recurring theme. So, loop invariance and the correctness of insertion sort. So figure 2.2 shows how this algorithm works. Where's figure 2.2? Here it is. So here is our list of numbers. Here above the list, we see the indices. So remember, j starts from 2. There is our There's our 2 right there. And our I is 1. So the element at the ith position is 5. So we're comparing the 2 and the 5, right? The index j indicates the current card being inserted into the hand, right? So you can think of everything to the left of j, everything to the left of this bar, as the cards in my hand currently. And I'm about to put this 2 in my hand. And I need to make sure that I put it in the right order. This is exactly what we talked about. The index j indicates at the beginning of each iteration of the for loop, which is indexed by j. Here's our for loop, which is indexed by j. The subarray consisting of the elements to the left of the bar constitutes the currently sorted hand. This is exactly what we noticed, right? Everything to the left of the bar was already sorted. And the remaining part, so everything to the right of the element that I'm currently looking at corresponds to the pile of cards still on the table. Okay, so think of it this way. You have a deck of cards. Some cards are already in your hand. They're sorted. The other card you just picked up, you looked at it. You're trying to put it in your hand in the right order. And then you have this pile of cards here still remaining. In fact, elements in your hand are the elements originally in positions 1 through j minus 1, but now in sorted order. Okay? Now, why does he say this? Why do they say these elements are the elements originally in those positions but sorted? Well, the reason they say that is because, look, how did we go through the algorithm? When we started, we didn't start by looking at this last -1 over here. We started by by taking the 3 into our hand, saying, okay, our hand is sorted. Then we picked up the 1. We found the correct place for the 1 in our hand. Then we picked up the next card, the -2. We found its correct place in our hand, right? There it was. Then we picked up the next card, the 2, etc. So we pick up the cards in the order in which they are in this deck. But as we put it in our hand, we put it in the right, in the correct, in the sorted order. We state these properties formally as a loop invariant. All right. At the start of each iteration of the for loop, the subarray consists of the elements originally there, but in sorted order. So this is all the elements to the left of the bar, right? Here was our bar. All the elements there are the elements that were originally there, the -1, the -1, the -2, excuse me, and the 1, but now they're in sorted order. Okay. So these first 2 here, if you look at these first 2, for example, notice 3, 1. These were the first 2 elements, but now they're in sorted order. If you look at -2, 1, 3, notice 3, 1, -2. These are the 3 elements that were in the array originally, but now they're in sorted order. -2, 1, -2, 1, 2, 3. These were the 4 elements in the array, but now they're in sorted order. So that's our invariant. Our invariant says everything to the left of the bar, is going to be exactly the values that were there in the original list, but now that they will be sorted. We use loop invariance to understand why an algorithm is correct, blah, blah, blah. Okay. Now our algorithm initializes. Initialization. It is true prior to the first iteration of the loop. And when they say it is true, they're talking about, what are they talking about? They're talking about the invariant, okay, the loop invariant. So let's start coding this up. And I believe as we code this up, things will become more and more clear. So I'm going to open Sublime Text here. Hopefully you can see this. Been doing some TensorFlow stuff. Let's move that out of the way. Save this. Let's put it on desktop. Let's make a directory called CS. And let's call this insertion sort. Okay, so we're going to make a function called insertion sort. What does it take? It takes a list. So I'm trying to follow the pseudocode as much as possible. So the pseudocode uses a to name their variable, and so will I. Now, again, what is our loop invariant? Our loop invariant is that everything to the left of the bar, everything to the left of the bar is the original, all the n values to the left of the bar are the original n values, the first n values, but sorted. Now look what they say. They say when we start our algorithm, that condition is true before our for loop starts. Well, when does our for loop start? Our for loop starts at the second index in our list. So remember, we started our for loop with the second element. So before our for loop starts, we have only considered the very first element in our array. And as we already said, if you only have one element, you're sorted. So that's why they're saying before the for loop begins, this loop invariant is satisfied. We are sorted before we've looked at the for loop, because before we've looked at the for loop, we've only considered one number. So it is sorted. Okay, good. Now, how do we maintain this invariance? Well, we say if it is true before an iteration of the for loop, it remains true before the next iteration. Okay, so what does this mean? This means that if this condition was true at the end of the line here, when I move to the next iteration, when my j moves one over, so when my j moves one over, at the end of this process, my this condition will again be true. Let's check. So look, when j was pointing to the second element, we were considering these two numbers, 3 and 1. When that process finished, we again had 3 and 1, but they were now sorted. So at this point, our invariance holds, right? Now, j goes over. We're considering 1, 3, and -2. When this part of the loop, when this for loop for this particular j value ends, our invariance still holds, right? We're still considering 1, 3, and -2, but now they're in the sorted order. So what does this show? This shows that from one iteration of the loop to the next, this invariance, and by this invariance, I mean the property that to the left of the bar, everything is sorted and consisting of the elements that were in those positions, that property holds throughout each iteration. When the loop terminates, the invariant gives us a useful property that helps show that the algorithm is correct. Well, so in other words, if this property holds for each iteration of this for loop, then when you're done with the for loop, your property still holds. So when you're done with the for loop, what happens when you're done with the for loop? Well, your bar essentially moves over here. This is when I'm done with the for loop, but my invariance told me that everything to the left of it are values, are numbers, that came in my original list, but now they're in sorted order. And that's exactly what I wanted to do. I wanted to sort those numbers, those 5 numbers. So again, this is you could analyze this mathematically and get all rigorous with it, but just intuitively, think about it this way. Everything to the left of the bar is going to be sorted for each stage of our process. In other words, for each position of j, everything to the left of that bar is going to remain sorted. So when j becomes 6, in other words, when j moves over here, here's our bar, everything in here is going to be sorted, and we're going to be done. Okay. And initialization, here they explain why j starts from 2, and this is exactly what I mentioned, because single element arrays are trivially sorted. So maintenance, how do we maintain the invariance? And we talked about the body of the for loop works by moving the elements to the left of the bar. by one position to the right until it finds the proper position to put our current element in. And we talked about this, right? We start when we're looking at a number, let's say j here is 5, so we're looking at the -1. What do? We start moving these values to the right by 1 until we find the right location to drop -1 into. And so because these elements all moved basically one step to the right and -1 was larger than -2, the correct order remained. Right? So from one iteration of the for loop to the next, we're retaining the correct ordering to the left of the bar. Okay. Short circuiting, etc. I leave this to you. Let's code this up. All right. Let's have the pseudocode so we can refer to it. So j starts from 2 and goes to the length of the array. Now remember, the pseudocode assumes we're starting the count from 1. In reality, in code, we start the count from 0. So we're going to say for j in range from 0 to the number of elements in A. Now, remember that this is not inclusive. So this is actually going to the length of A minus 1. So if my A has 5 elements, this is going to go from 0 to 4. Okay. So for each one of these j values, what do? I save the key. Now, notice, we want to start the j, as we said, right? The one element array is trivially sorted, so we want to start the j from the next position. So I want to start not from 1, but not from 0, but from 1. So from the second element in my array, not the first element. So I save this inside a thing called key. Here's my key. Save it in key. Comment here, save the jth element of A in a variable called key. What do we do next? Now, here's the process. So we need to find the place of that element in the sorted sequence. In other words, to the left of that bar that we drew. So how do we do it? We need to compare, right, to the element to the left of it. We need to start comparing first to this element and to this element. So what is the index of this element? Well, it's 1 to the left of j. And that's what this says right here, j minus 1. So we start. So let's say find the place to the left. Find the correct place for key to the left of the bar. Okay, so I will be j minus 1. Now, as long as I is bigger than 0 and ai is bigger than key. Okay. So I'm going to type this up and then we'll talk about it in a second. So for as long as I is bigger than 0 and a sub I is bigger than key, what are we doing? This is where we're comparing, right? We're saying if the so here's our comparison. So if this ith element is bigger than key, what I'm going to do is I'm going to put that element in the I plus 1th position. I'm going to reduce I by 1. So let's write clear fashion I equals I plus 1, like so. So this process, so okay, now what do I want to, I told you I would type this up and then we'd talk about it. So let's talk about it. Let me make an example. So let's suppose we have an array here that is in reverse order. Let's say -4 and -3 and -2, let's say. So just sticking to now real indexing. So this is the 0th position. This is the first position. This is the second position. So this is our j in the beginning, right? This is our j. I don't know why I'm using the mouse and not the pad. So let's go back to the pad here. So this becomes our initial ith position. Notice that I is 0, right? So we compare, is -4 smaller, or in other words, is -3 um, smaller? Well, this is not in reverse order, is it? Make sure it is in reverse order. Let's, let's do -2, -3, and -4. Okay, so here's my j, which equals 1, and here's my I, which equals 0. Okay, so now we start the comparison. We say, is -2 bigger than -3? Yes, it is. So -2 gets pushed over into -3's place, like so. But now I needs to go back one more step for me to realize that my array has ended. Basically, I'm done. There's nothing to the left, so that I can put this -3 in this position. But when I move I1 over to the left, what does I become? I becomes -1. Notice that in the pseudocode, the condition is that I has to be bigger than 0. But this is the case because they start the count from 1. We start the count from 0, not 1. And so for us, I has to be bigger than -1, right? Because the indexing is from 0. So I has to be bigger than -1. So as soon as I becomes -1, my loop ends. And I know that I'm going to put this -3 into I plus 1th position. See? I plus 1th position. In other words, the 0th position. So going back to our code here, this needs to be -1 and not 0 for us. That's the point. I hope that made sense. If not, again, draw out an example for yourselves, and just remember that we are starting the count from 0. The book starts the count from 1. It is ridiculously confusing at first, but you get used to it. All right, back to the pseudocode. Um, So now we've reduced I by 1, and we were doing these comparisons, right? We're doing these comparisons. Where are we? Let's go here. Where here we pick the -1. We start doing these comparisons. 3 is bigger, 3 gets pushed over. 2 is bigger, 2 gets pushed over. 1 gets bigger, 1 gets pushed over. -2 is smaller. -2 is smaller. Our loop stops. And into the element after the -2, so into the I plus 1th position, into the I plus 1th position, I put my key. At this point, we have found location, put key here. Put variable key here. Okay? So this should do the trick. Now let's give this a go. I'm going to go to desktop. I'm going to go into CS. Let's see, there it is. Let's start up our interpreter. Let's import this. So let's say from insert. Actually, I don't know if you can do this. Let's do import insertion sort as sort. Let's see if it'll let me. It lets me. Great. Okay, cool. Now let's make a list. So our list A will be. Let's actually use the example that we did by hand here, and it had the numbers 3, 3, comma 1, comma -2, 2, -1. There we go. That's my list A. Let's now try to sort it. So I say sort. Well, there's going to be an issue here, and the issue is that, let's see. So let's say sort dot insertion sort A. Hey, look at that. Our array is sorted. Let's try another one. Let's try an array consisting of the elements. Let's say A equals, let's see, I've done a different example here. Let's go pick out, What is this? This guy. -3, 4, 0, -5, 7, 8. Close. Let's do insertion sort on this guy. Run it. It is in sorted order. So it seems to work, right? Well, remember that I mentioned this corner case when our array has only one element, because this algorithm says start the for loop from the second element, because we assume that, because I mean it's obvious that the single element array is automatically sorted. And so when we're looking at an array, if I put the bar here, if I were, so I start my j here because it is obvious that this part is already sorted. It has only one element, it is sorted. So what happens if I run my algorithm on an array of size 1? So let's say a equals array that just has the number 1 in there. Let's now try to sort this. Sort insertion sort a, and it works. How? Well, let's go back to our code. So what does our code do? Our code says start j from 1. Start j from 1 up to, not including, the length of 1, right? So if, for example, I'm going to write this in comments here. If, let's say, my A consists of the list 1, 2, 3, and I want to sort this, so j starts from 1. J will be in 1 up to 2. Why 2? A has 3 elements. Why 2? Because remember, length of A not including, non-inclusive. So len A is 3. We're going from 1 to 3, non-inclusive. That's 1 and 2. Now, let's do another example. Let's say A has 4 elements, -1, 2, 3, 4. What is the length of A? Length of A is 4, right? We have 4 elements. That means this expression, range from 1 to len A, is essentially the same as saying range from 1 to 4. But remember, this is non-inclusive on the right side, so this is going to be 1, 2, 3. Why is this important? Because when A has a single number, and the range from 1 to len of A is the same as the range from 1 to 1. Notice non-inclusive. This one is non-inclusive. So it says basically start from 1, but then go up to 0, inclusive 0. Right? So we don't even have an interval there. We can't put an element here. It says like start at 1 but go to 0. We're like going backward. The whole universe collapses. So this is just an empty list. Okay, there's nothing here, and we can check this. If I say range, or if I say give me the list of the range from 1 to 1, what does it give me? It gives me the empty list. Whereas if I told it to 3, it would give me 1, 2. If I told it from 1 to 10, it would give me from 1 to 9. But from 1 to 1, because of the non-inclusivity of this right digit, that's just empty. And because this returns empty, the for loop is never executed, right? Because this for loop says for. Oh, I apologize for these yellow lines. This is Flake8 going crazy. Let's do this. So because this returns the empty, this list here is empty, and j goes through the elements in this list, this j is never set to any value. So this for loop is basically never executed. So our function doesn't do anything. If you give it a list of 1 element, doesn't do anything. If you give it a list of no elements, then len A will be 0. And again, this is like going backwards. There's no interval to go to. So again, the for loop is never executed. So if I try to run my algorithm on the list of no elements, this again will not do anything, right? So if I set A to, let's say, empty list, run it, and say what is A, it is still empty. Okay. So this is a nice feature of Python. Now, this is language dependent. So if you're coding this up in C, C++, or Java, or compiled languages in general, something that's not made for quick prototyping, really, you might have to set an extra condition. You might need to say, if len a, for example, if the length of a is less than 2, return a, right? So, or pass or something, right? So, or you can put this whole thing, you can say, if the length of a is bigger or equal to 2, get this, and toss this inside the if statement. The reason I took out the return statement is because I realized this is a destructive operation, right? We're modifying the A. Remember, this is in place. We're modifying the actual array, so I don't want to have any return statements here. So what I'm saying is apply this algorithm, apply insertion sort only when A has more than or 2 or more elements. So you might have to apply this logic if you're in some kind of compiled language. In Python, however, this range, this range iterator here, or yeah, it gives us this nice feature in that if this is empty, then the for loop is just never executed, which is what we want. Okay, so that is insertion sort. So remember the idea of loop invariance. Loop invariance, you at the beginning of the algorithm, the very start, you establish your invariant, then you convince yourself that through each step, each iteration of your algorithm, the invariant is satisfied. And then you, based on, and if those two conditions hold, then most of the time, your invariant will hold at the termination of the algorithm. Very rarely the termination messes things up, and you have to check at the very end of the process that your invariance still holds. Most times it will. So if at the beginning it holds, and then through each step it holds, it usually holds when the process ends. It's sort of like mathematical induction. Okay, so I strongly suggest now you go through these exercises. We have, let's see, 4 problems here. I strongly suggest you go through them. I will be going through them myself. And if you have any questions, do post them on the in here in the stack. What stack? What am I talking about? In the Discord channel, and myself or others will be very happy to help if we can. All right, guys, have a good evening, and I will see you next time.